You know, no one's ever really gone. I'm Palpatine. Hello and welcome to another edition of Because Science Live. I want to tell you just how impressive it is to actually see a black hole for the first time. So by this time you probably have seen the first ever images of a black hole, and they look something like this near perfect rendering I have for you here in the void. Now, this is incredibly impressive, and I'm going to explain to you why, but on the face of it, let's admit it, this doesn't quite look like any black hole you've ever seen rendered by an artist or in any sci-fi anything. It can seem a little lackluster if you compare it to something like Interstellar, but I want to prove to you, just with some numbers, which you know always interest me, why this is just so impressive of an image. First of all, we are observing an absolute monster from an enormous distance. So this black hole, the M87 star black hole, exists within the M87 galaxy, which is in the Virgo constellation, which is 55 million light years away from Earth. Now, we'll get to that number in a second, but that's a very long way away, so it's hard to see things that are that far away. Secondly, this black hole is one of the largest, most massive objects of this type that we have ever seen, ever. It is a few billion times more massive than our sun. And if you had to compare this image of the black hole that you've seen to Earth, to the sun, and to the solar system, it would look something like this. There's the sun. Oh, sorry. And here's the orbit of Pluto, just about. So that should give you a little bit of the sense of scale that we're talking about here. The entire solar system would fit within the maw of this thing. This is a supermassive black hole, and it is an absolute beast, taking in matter, eating it from all directions, creating this giant accretion disk and spitting out high-energy jets of plasma and stuff that, you know, extremely high speeds for light years long worth cones. Anyway, you can tell I'm getting kind of flustered about it because it's so cool. Anyway, so this thing is an absolute beast. The other part of why this is so impressive as an image is just how hard this thing is to see. So like I said, it is 55 million light years away, but it is extremely big. The problem is despite how big it is, from that distance, it's very, 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 very small in the sky. And when we talk about how big things are in the sky, astronomically speaking, we talk about something called like an angular resolution, an angular distance. How big is something in the sky? Well, we have an equation for this, where you have a constant, some conversion factor here, but the angular distance is a factor here, and then multiplied by the diameter of the thing, the actual diameter of the thing that you're trying to look at, and then divided by the distance that thing is from you. That will give you a relative size in the sky, usually in degrees. This one will be in arc degrees, which is, we'll get to that. So 1 degree in the sky, if you hold up your pinky and you hold it up to the night sky, your pinky is about 1 degree wide. So, you know, something like the sun is many degrees in the sky, and anything smaller than your pinky is smaller than 1 degree. Now, 1 arc second, which this equation will give us, is 1/3600th of a degree, and it gets even smaller than that. So let's do the equation. So we have this factor here. The diameter of this black hole is enormous, as you can see from how it dwarfs our solar system. It's billions of kilometers across, and it is 55 million light years away. And if you do the math, roughly speaking, you can get a value close to what's reported in all of the journals and papers, etc. And you get somewhere in the neighborhood, you know, 10 to 40 micro arc seconds. Now, I said an arc second is 1/3600th of 1 degree. A micro arc second is 1 millionth of 1/3600th of 1 degree. So you can tell this is extremely, extremely small in the sky if you were trying to look at it. In fact, it is so small that an equivalent of being able to see something in the sky would be if you could see my fist on the moon. If I was standing on the moon and trying to one punch at you like, Saitama or something like that, you'd be able to resolve my fist, something this big, on the surface of the moon. It is extremely, extremely small. That's the other part of how impressive this is. We don't even have a single telescope that can see this thing. What actually saw this black hole, another reason why it's so impressive, is that it took many different telescopes observing this black hole over a period of time across the globe, making effectively a telescope the size of the Earth just to see this because of how small it is in the night sky. And it was recording so much data to put this together. It was 350 terabytes of data per day. And so, 350,000 gigabytes per day to put this all together, and it was many days of observation. And they needed a supercomputer to take all that data from all the different telescopes and combine it to resolve this image. The hard drives they needed to use, because they couldn't transport this data across the internet, it would take literally an entire month to transfer all this data. The hard drives that they used were helium filled. They filled these hard drives with helium because many of these observatories and telescopes were at altitude to eliminate some of the atmospheric disturbances that these telescopes would encounter. So they were filled with helium so they could operate at higher altitudes rather, and so they'd be more precise in writing on the disks, because moving through helium, the writing process, there's actually less turbulence than moving through regular old air. So they had state-of-the-art hard drives from an Earth-sized telescope looking at something 55 million light years away that is so big it dwarfs our solar system, giving us the very first image of a black hole. It was an absolutely amazing amount of scientific power and resolution, imaging an absolute monster of an astronomical object. And it is absolutely, no matter what it helps prove for physics and stuff like that, it is an absolutely amazing feat that we, as mostly hairless apes on the surface of, on just the outer crust of a blue marble somewhere in the universe, that we were able to do this. It's absolutely amazing, no matter how blobular this may look on the face of it. Woo! Hello and welcome to another edition of Because Science Live. I already said that, but this is the live edition of this channel, as you may have suspected, where I take all your comments, questions, corrections, and comments about, how I do things personally, and I try to address them off the top of my head. Look, I'm not an astronomer, I'm not an expert or a working scientist, but I know a little bit about a lot of sciencey things. I do have a background in science. A little bit about a lot of sciencey and pop culture-y things. So if you have any nerdy questions you can think to ask me, I will try to answer them to the best of my ability, but if I do not have one, I will either redirect it so it's a question that I can answer, or I will totally punt, or I will refer you to something else you can watch. So with that, I have Nate somewhere around here.
Yeah, I'm here. What's up, Kyle?
Oh, okay. What's first?
Nice Palpatine voice earlier, too.
Oh, thank you. He's back now, somehow.
I got a couple of black hole questions for
Okay,
you.
well, like I said, I know as much as you do about it, so I'll try my best.
From Rog Grotto.
Okay.
If black holes suck in light, how does that have any color spectrum?
Sure. So we were looking at this with radio telescopes. So a lot of the light that we were getting from to make this image wouldn't be light that you could actually see with your own eyes. But what's important to point out is that the black hole part that you actually see is the shadow of the black hole, because as you say, no light is escaping from the black hole. What we see is kind of like the shadow or the outline of it, especially from all this globular stuff on the outside of it, the accretion disk, all of the interstellar gas and matter that's being sucked into the black hole. And as it does that, it accelerates and accelerates and gets really, really hot, gets so hot that it starts emitting light. And so we can see that kind of light. But we saw this, I believe, mostly with radio telescopes. So you doubly can't see it. So we see only the shadow because light can't escape, and a lot of this light is coming in the radio part of the spectrum, so you can't see it with your own eyes. That's another part of why this is so amazing, though, if you think about it. being able to use telescopes to see something invisible with an Earth-sized telescope 55 million light years away. It's incredible. What's next? I would recommend my legal guardian, Derek Muller's video, Veritasium. I would recommend his 2 videos on the M87 black hole. They are very, very well done. And hey, good for you, legal dad. What's next? I'm starting a rumor.
From Lisa Sky.
Hello, Lisa.
How is a black hole formed?
How is a black hole formed? Well, if a star dies and it has enough mass, when it dies, it can have so much gravitational attraction in the core when it gets compressed together. Usually, if something goes supernova or something like that, what can be left is a stellar remnant, something like a neutron star, which, as you know, if you watch this program, is an incredibly impressive object. And the highest amount of magnetism of anything that we know of, the densest anything that we know of. It's basically just nuclear matter pressed together. They're incredible objects. But if you have more mass in an even smaller space when a star dies, it can go past neutron star and into black hole. There's so much gravity that it just collapses in on itself and in on space-time itself. And then you have this gaping hole in space-time where nothing can escape from. And we always look at it like this, and we see it in sci-fi and pop culture and what have you, like this, like a 2-dimensional image. But if you rotate a circle in 3 dimensions, if you look at something from any angle and it looks like a circle like this, that means it's a sphere. So it's a hole from every side, which means that it's more like a black sphere that everything goes down into, if that makes sense. When something has enough mass from something like a star dying or what have you, or maybe another star is too close to another star in a binary system and it's siphoning gas and matter away from that star, it can get so much mass, it explodes, so much mass in a small amount of space, forms a black hole just from the gravitational collapse of the thing, where well, if you want to get technical about it, when the neutron degeneracy pressure of something like a neutron star can no longer push out against the forces of gravity, and we don't even know what happens at the center. The laws of physics seem to break. Crazy. And it validates, and this image, validates some of Einstein's theories and stuff like that. It's amazing. What's next?
Kind of branching off of that.
Okay.
From Violet Valhalla.
As you can tell, I'm doing okay so far, but
Yeah.
one of these questions is going to break me.
Did we learn anything new or verify anything with this image?
So I don't know that off the top of my head. I do know that I just read that some of the observations of the M87 star black hole fit with predictions about what a so-called Kerr black hole should be. It's a rotating black hole. I think it's spinning. I forget which direction it's spinning, but it's spinning on an axis. And so this image of a black hole and what we can gather from it, again, I'm not an expert, but what you can gather from the intricacies of this image and from the observations that were done fits with predictions about what a black hole mathematically should look like, be like, act like. So it's not just an image. It goes a long way in proving some of our theories and some of our predictions, which is incredibly important in science, because if you actually observe something, that you do that experiment and your theories don't fit with experiment, your theories are wrong. That's what Richard Feynman said. So this is very important in checking ourselves to see if our understanding of the universe is actually correct. And we did it with something like this. It's just cool on every level.
All right, moving away from the black hole for a little bit.
Thank you. I was waiting for someone to say something.
From Fartakuno Boy.
Okay. Fartakuno?
Yep.
Really?
It's great.
Fartakuno? Really?
What would happen if we could focus all the sunlight in one single beam of light on Earth?
Like a giant magnifying glass kind of situation? I may be getting, so I'm gonna pivot a little bit, and I may be getting this wrong, so I will refer to what I'm going to refer to. But if you have, let's say, I think you're talking about more of like a magnifying glass situation. And if you had something, these two things are on different scales now. If you had something like the sun that was emitting light and you wanted to focus it all down into one spot, you would want to, since it's coming out in all directions, what you would want to do is have some kind of focusing mechanism like a lens. And this lens this giant lens in space, this is a supervillain kind of thing now, this giant lens in space will take those beams of light, and if you have the right size lens, it will focus them all down to a single point. Now, like I said, I don't know exactly this off the top of my head. I know it would be very bad, but I will refer you to, I think XKCD and Randall Monroe answered this exact question. And the only thing that I remember off the top of my head is that you cannot focus light from a source to be more powerful than the source itself. Right? So not more powerful than the total source. So if you had a flashlight and you took all the beams from a flashlight and you put it into and you put it through a lens at the one focal point on the other side, the intensity might be higher, but it's not going to be more than the sum of its parts, so to speak. So basically what you're saying is what would happen if you took the normal intensity of the sun all the way around and put it down into one point. It would be bad. The amount of power, yep. The amount of power that the sun hits the earth with when it gets all the way from space, all the way through our atmosphere, when it gets down to the surface of Earth, it's around 1,030, which I know no one says it like this, about 1,000 watts per square meter. And 1,000, you can feel sunlight, right? And it's pretty hot, on a summer day. Now, if you focus this down so that, you change the size of the area that you were talking about, focus this all down to, say, a square millimeter or something like that, you can get an intensity that will burn stuff. And you can do that. Don't do that with ants or anything like that, but you can burn a piece of wood, a piece of paper. So if you focused all of the beams from the sun down into a single point, it would have, it wouldn't be more than the sum of its parts. It would just still have the energy output of the sun, but it would just be down in a single point, which would be very, very bad. I do not know how bad it would be off the top of my head. I will refer you back to XKCD's explanation of that, which is somewhere on the internet. Google it. What's next?
A little maintain question for you.
Oh, wonder why.
From Nick Lepsy.
Hello, Nick.
Is your hair naturally straight? If not, how do you straighten it? Additionally, can you provide maintenance advice for someone who has wavy/frizzy hair?
Oh, see, now this is getting a little outside my ballpark. All right, so I got a natural little bit of a wave, but what I like to do sometimes is that you can you can put your ponytail in a certain way on the back of your head so that it gives you a little bit of a bump, see that little bit of that curve, a little bit of a wave, so it's not just straight. My hair is basically naturally straight, a little bit of a wave. If you have curly or frizzy hair, it's out of my ballpark. I don't want to give you bad advice on that because I've never had to straighten my own hair with a hair straightener. I do not know how to use them, and they scare me because I see significant others burning their face and neck all the time with hair straighteners, and I do not want to mess around with that. So if I had to give you any advice, it would be, and this is what I always learn, go to the people, look, dudes, I know it can be kind of a hit to your ego or whatever to go to someone who actually knows how to take care of their hair and say, hey, can I not look like crap anymore? But you need to put that aside. You need to start investing in things like great conditioner, hair dryers, argan oil. Go to a salon where they know how to deal with long hair, and just leave your ego at the door and just say, look, I need some advice on how to do this. Because we gotta stop looking like we're playing bad rock and roll music in high school. Look back at your photos. I said never again. It's my advice. Take care of it. Take care of it. Do the things that you think might not be, and I don't want to get in trouble here, but some things can be considered. If you're a man with long hair, or as someone who identifies as male with long hair, you can feel like it's not manly to do blow drying or straightening or what have you. But leave that at the door. You look good. You want to feel good. Yeah. What's next?
From Alexander Charlton.
Okay, sorry. I thought I knew you, but I don't. You're just a stranger to me.
If you could battle any sci-fi/fantasy monster using any sci-fi/fantasy weapon,
whoa,
what would you choose and why?
Whoa. Okay. That is a very difficult question. But I would, the first thing that comes to my head, I do not know why, is fighting Galactus with that weapon in Ender's Game that has a chain reaction. When it hits something, it can blow up an entire planet. I would like to shoot that right at Galactus's face. That's what I would go for. Or the second thing that I thought of immediately, I don't know why, was plunging a lightsaber into that octopus that guarded the door in Lord of the Rings. Ah! Who wants calamari? They cut that line.
All right, moving on. From Red Fox 1562.
You didn't want to hear any more of that?
No, I'm good.
Okay.
Could you see a black hole with a naked eye without being pulled into it?
Yes. Yes. I mean, so again, like we were saying before, seeing a black hole is kind of a complicated thing to say, right? We're seeing where the light would be. You know, you're not seeing an actual object because no light is bouncing off of the object and coming back to your eye. So you're seeing the absence of light, which we can call a black hole if it fits, the criteria. So, can you see it with your naked eye? I would guess yes. If you were in this regard, I believe Interstellar is quite accurate. Where if you were far enough away from the accretion disk of a black hole, let's say you were near the galaxy M87. Say you were near the core of M87, and you were therefore near M87 star here. If you were sufficiently far away from the accretion disk, such that it wasn't vaporizing you with radiation and whatnot, it would be very bright, and you would be able to see where all that accretion, where all that matter was going. And I think, again, not an expert, but if Interstellar's correct, I've talked to the guy who helped write the script, Kip Thorne, who just won a Nobel Prize for LIGO and for detecting gravitational waves, depicting a black hole in this way. There's probably some distance at which you could be from it and not immediately die. How close you would have to be to it, I do not know. This kind of reminds me of how close can you get to a neutron star without dying? And I have read a paper on this where could there theoretically be a system that used a neutron star just like a normal star, like our sun? And yes, there is theoretically some distance at which a planet could be that it would get the same intensity of radiation that our sun gives us. So, neutron stars still put out radiation in all directions. So there is some distance you can be away from a neutron star and not die. I would have to guess, even though black holes are monstrously dangerous and scary, but also cool, there is some distance you could be away and still observe it in some meaningful way so it doesn't just look so blobular. But I do not know how close you could get. Not close to the event horizon, I'll tell you that. Because spaghettification is only a word. The reality is much worse.
Nice.
That's an event horizon reference. I think I did pretty good.
Yeah. That was pretty good.
Thank you.
From W. Basin. What are light years?
What are light years? Very simply put, a light year is the amount of distance that light covers in 1 year. It is a useful unit because space is so big. Even something going at the speed of light, 300,000 kilometers per second, 300,000 kilometers per second, even that isn't fast enough to get even to the nearest star very quickly. The nearest star is 4.3 light years away. So we use the term light years, how far light can travel in 1 year, to help us shrink some of those distances, so to speak, so we can talk about them and don't have to say million, billion, trillion all the time, if you're just using meters. So it's a convenient unit, just like using something like a parsec is a convenient unit of distance. A parsec is a little over 3 light years. 3.26? It's a little over 3 light years. So that's another convenient way of shrinking distances down, relatively speaking, so you can talk about them and not have to say these long numbers. Because if we used inches, feet, miles, kilometers, it would just be, the distances would just get too large. So you can say parsec or whatever. And astronomers even use like kiloparsec or megaparsec because space is just so big. 55 million light years away. See, you still even have to use millions of light years to describe these kind of things. So that's why we use that unit, and that's what it is. One more?
Yeah.
Oh, okay.
We got a couple quick ones if you want to do them.
Yeah.
From Austin Herman.
Hello.
What's your favorite part of being a science communicator?
My favorite part of being a science communicator, if I had to pick anything, the work is hard. This is my day job. I do 9 to 5, this all day, every day. The payoff for me is seeing anyone engage with the material in a really meaningful way for them. And some of my favorite things to hear about or to get or receive or whatever is, an email from a teacher that says, hey, I played your video in my classroom, or I've gotten tweets with images showing, someone's baby girl watching me on their TV, through YouTube or something like that. I want everyone to enjoy what I do. I try to make it as enjoyable and as educational as possible, but my true goal is education because I'm just as excited. I'm so excited about this kind of stuff. I hope to make some of you that excited as well. So when I see people engaging in that way, it really warms my heart, and that's one of my favorite things.
Cool. You got one more?
Oh!
If you could, from John73 John.
Where are you speaking
I'm
from?
everywhere.
Yeah, okay.
If you could be on the Expanse, would
Yes.
you want to be an Earther, Martian, or Belter? Also, what job would you want?
Okay, so I love The Expanse. Go watch The Expanse if you haven't yet. It's now on Amazon, streaming seasons 1 through 3, and then they just wrapped season 4. I don't work for them, I just want to. So if I was in The Expanse, what I really like about it is that they have different physical characteristics for people living on different surfaces. So if you live as a Bauta or something like that on the asteroid belt, you're more lanky, more skinny. You're also taller because of gravity on something like an asteroid, even if it's spinning, and they spin it up to get gravity. The gravity isn't as much, and so you kind of extend outwards like our astronauts do when they go to the International Space Station. They get a little bit taller. Martians live under 1G, so they have to train under different gravities. They train under 1G just in case they ever have to invade Earth. It's all great world building, and I like it. But I would probably be. I'm not very combat oriented. And I'm not that much of a thrill seeker, so I'd probably be someone on Earth trying to, figure out the best Holtzman transfer to sling myself around Mars kind of thing. I don't know. I would love to be just a passing scientist with a really cool hairdo, because it's from the future. That's what I would be. Oh, that's it.
That's it.
Thank you so much for joining me for this edition of Because Science Live. I hope that you've had a great week so far. Thank you for watching. Thank you for watching the Thanos butt video. Wow, we really did it. I know a lot of you have comments and questions about that video in particular, so if you want to see more of that, I will try to address many of your comments, questions, and corrections in the next episode of Footnotes, which is on Tuesday. We have a new episode going up on Thursday, which is something a little bit special, which I hope you're excited about, and then another live stream on Friday. Also, we have a new episode of The Science of Mortal Kombat on Monday, episode 5 out of 6, and this one, is going to be a doozy. We try to uppercut someone so hard that they fly above our heads. Spoiler alert, that's pretty hard to do, but you're going to want to check out everything that Alan and I get up to on that. So have a wonderful rest of your weekend, and remember, with perspective like this, massive scale so far away, be nice to each other, because right here on this planet right now, this is all we got.
Merman, baby! That's right, the truth is out there. Done told you.
Dan, I dressed up for this.
Stop trying to make Merman happen. It's not going to happen. We just don't have enough time.
Well, there are 6 episodes left, and if they're all feature-length, feasibly we could see Varys reveal the truth beneath his robes. After all, the phrase Valar Morghulis comes from the original Valar Morghulis, and Valyrian steel might not be enough, but the night is dark and full of secrets, and what could be more secretive than fishy parts down under?